So let's say you have your microcontroller for your project, and it's great. It's got all the processing power and memory you could possibly want. But you know the saying, no microcontroller is an island, or at least something like that. It's going to want to know the time, what the weather is, how bright it is, and it's going to want to tell you all these things, of course. So perhaps the easiest or most straightforward way of pushing your data around is to literally push it down several lines. Say you have an 8-bit word, you can just set the high and low bits directly into 8 lines and pass that along. We only need a couple more lines signifying when the data is ready to be read, and it's as simple as that. And of course, the best thing about simple is fast. You can pass an entire 8, 16, even 32-bit word along in virtually a single clock cycle. This is why you'll see embedded LCDs and memory components using parallel buses on circuits. It's also the reason why, for the longest time, we had to put up with hard drive cables the size of duct tape before we managed to get serial fast enough. But what if we don't need speed for our devices? Or rather, if the chip we need to talk to about temperature is all the way on the other side of our board, our 8 data lines are going to be somewhat overkill and going to get tangled up pretty quickly. The next logical step is lining up our data serially. We only need to take our data, add a stop bit, and it can easily be pushed out 1 bit at a time. Obviously, this method isn't new, the most widespread use of it being the RS-232 protocol. Though you won't see the RS-232 serial ports on most devices nowadays, they've taken a backseat role in hardware. You can still find RS-232 style serial in TTL 5 or 3.3 volt levels on other devices. Things like routers, game consoles, TVs, Twitter-enabled smart fridges will likely have an internal connection allowing for low-level command access and debugging straight to the microcontroller. We have several benefits to this protocol, like being able to asynchronously send data without worrying about clock speeds, or sending 1 or 2 parity bits to check for errors in our transmissions. In fact, this serial protocol is what the basic Arduino is built around. When you have an Arduino and you connect to a USB, you're most likely connecting to a USB to serial interface. The actual Atmel chip on board is preloaded with a bootloader to accept compiled programming data over its serial interface and write it to flash memory. So we have a solid serial protocol for talking between 2 chips, but what if we need to get more than just the temperature? Say we have a chip that knows the temperature, another for the humidity, and another for how bright it is outside our device. Now we could run 3 separate serial transmit and receive lines to all 3 devices, but we're running back into the problem we had with our parallel bus of having overkill and a mess of wires. This is where we can use an SPI bus. With SPI, we still have our transmit and receive, now called master out, slave in, and master in, slave out. In addition to our serial lines, we also have to send out a clock pulse down a line called the S-clock. This is more for the benefit of devices we're talking to, because now it does not need to worry about keeping track of asynchronous data flying at it. It knows exactly when to receive and send data. The 4th line is the slave select line to tell a component when we want to send and receive data. So in order to talk to many chips, we need to add a slave select line to each of our devices. If we want to talk to a specific chip, we set an active low to that specific slave line. The slave chip then listens up for the serial data on the serial line while the rest of the chips ignore it. So we have a way of talking to multiple chips with serial data. That's good news as our design demands even more devices our microcontroller has to talk to. But as things go, we can see we're running back into the same problem we had with the mess of lines to manage, even with a single serial line. This is where we would want to use I2C. With I2C, we combine our transmit and receive line into a single data line called the SDA. We still send out clock pulses down an S-clock, but instead of having individual lines to control who we talk to, we take care of that with addresses built into our components. Our master microcontroller now has an extra word of data to send with every packet of data. We announce the address of the chip we want to talk to down the SDA line. The device with the matching address listens up to the data attached to it, while the other devices that don't match the address ignore it. If we need to receive data, we send out the address we wish to speak to and the address of the register on the chip, along with the stop signal. A component would then send back after receiving us the data we requested.